we've already taken a look at this. And as soon as you guys leave, I'm going to record our online lecture for the week, which will be where we pick up where we leave off. So kind of hovering in this chapter, and this will be the last chapter that we do before the exam, which will pop up next week. So just kind of keep that in mind. If you have any questions, just let me know. We'll have a second review quiz posted tomorrow morning. I think you know the routine there. So again, just let me know if you have any questions.
Is the online lecture part of the quiz?
Oh yeah, absolutely. Yep. So yeah, you want to watch that before, right?
Yeah.
It'll be kind of what's left over of this chapter. Well, actually not all of it. We're going to save some of that for next week too. So I don't want to go too much further than where we're at before we do that first exam. And it's a little bit different. So I'm not doing the screentastic thing, however you say it, screentastic, whatever that is. I don't really like that too much. So I'm just going to use the PowerPoint. I'm going to not do the video though, however, because that makes the files like just massive. So if you happen to be not in a ultra high speed internet zone, you might have a hard time downloading it. So it'll just be a PowerPoint presentation, which works a little bit better. That can be a little more interactive rather than just sitting there. You'll see. So all you have to do is download it and then just hit begin slideshow and sit back and enjoy the show. So, and if you have any problems, just let me know. Why wouldn't you? Hopefully you would. But we're starting here. We still have a little bit of mop-up work to do. There was a lot for you guys to watch. A lot for you guys to watch last week with regards to trying to live, right, extend our lifespans. All the stuff from transhumanism and all that stuff, and the people that are trying to make you live forever, essentially. But here's what I want you to know. I think I told you last week we would spend a little bit of time kind of mopping up the stuff. So you might already have some of these notes just from watching those videos and taking notes on them, like I'm sure you do. But in case you don't, here's what I want you to know. So 2 camps, right? 2 camps that are kind of divided in the field of adulthood and aging. One camp says we're going to die and we're hardwired to die. That's part of us. The other camp says no, aging is the disease. So let's zoom in on the first camp, the programmed aging camp. These are the folks that say aging and getting older is just a natural part of not just our lives, but of all organisms. It's hardwired into us. And hopefully you picked up from the one of the online lectures last week was behavioral genetics and the idea of heritability estimates. We've actually figured out, so think of your own family tree. Do you have people that live until their 90s, maybe 100? Or do you have people that die in their 70s and their 80s? Maybe you've wondered, is that predicting how long I'm perhaps going to live? We've actually figured out the heritability estimate for longevity, and it's 0.25. In other words, 25% of your longevity is intertwined in your genetics, which may or may not be good news. But just for some free review, would you say longevity is plastic or constrained? I went over this and see if you were actually watching that. So behavioral genetics, heritability estimates, 0.25 would be the HE. Is that plastic or constrained? You look like you're going to say something.
Well, I have a question on that.
Perfect.
I was in the video, I don't know if you listening to it wrong. I thought you said constrained and plastic are both based on the environment. Okay,
well, perfect. I'm glad you asked. So with heritability estimates, right, if something, it's weird because it's all on a number from 0 to 1, right? And the closer to 1, the more genetically constrained something is. If it's closer to 0, the more plastic and malleable it is. So we've actually figured out, let me use an example for you. So human height has an HE of 0.8. So in other words, your adult height, it's 80% genetics. That's a very constrained characteristic. In other words, the environment plays a role, but not very much, only about 20%. Longevity is very plastic. It means it's very malleable. Only 25% of your longevity is in your genetics. So we call that a very plastic characteristic. So anything below like 0.6 would be considered pretty low and pretty malleable. Does that help?
Yeah.
All right. So if it's a high number, like 80%, it's like 0.8, 0.9, that's constrained. Something low, like 0.2 or 0.3, would be very plastic. And we just use the word plastic because it's changeable, it's bendable. So again, this might be good news, might be bad news. I'm not sure how long people live inside your family, but the message is 75% of your longevity is up to you and the choices that you're making and the kind of life that you're going to live. I see that as kind of positive because that means more or less you're in charge of what's going to happen to you. Quasi, there's a few things that they use to support this idea that aging and dying is inevitable and it's hardwired into us. One is an old idea called quasi-programmed theory, which seems to hold up. When do we get most diseases that might knock us off the planet? Things like cancer. Do we get them as little children, or do we get them more as older adults? Of course, older adults. And this is why, of course, children can get these diseases, but that's why it's so heartbreaking, because it's not supposed to happen. We're much more likely to get those diseases. In fact, as the years tick by, our risk for everything goes up, right? Over 60, risk for stroke, risk for heart attack. Quasi-program theory says that as you develop, there are genes switched on in your body that help promote growth, that help promote a strong immune system, and help promote repairing of your cells. This is true. This is not untrue. Especially when you go through puberty. It's not like you're invincible. Of course you can still get sick. Of course you can still get diseases. But a very realistic example that I always use just comes from my own universe of distance running. I still do it, but I remember in my 20s, I could run a marathon and be really, really, really sore for like 2 days. Like I can't walk up steps and this really hurts. Now, when I'm 43, I can still run the same marathon, but now it takes me like 2 weeks like to even come back to some sense of normalcy, because it just takes my body longer to repair everything. I can still do it. It's just the repairing part takes a little bit longer. That's exactly what quasi-program theory says. You've got these nice developmental protective genes switched on while you're developing, but then when you're done developing, they switch off. That's quasi-program theory. In other words, we have genes that are turned on in our body that protect us for a limited amount of time, and then they slowly switch off. They also rely on something else that is very true called replicative senescence. What this means is the stopping of the replication of your cells. Right, this is how we keep going. Our cells replicate themselves. Your DNA replicates itself. Well, we do know that a cell can only replicate about 50 times. That's it. After about 50 times, it's done. So it seems, even on a cellular level, that there's a finite number of times that our cells can replicate and replicate correctly. And why is that? It all has to do with this word right here, the telomeres. If you look, this is, of course, is a picture of a chromosome. The telomeres are here, indicated in the red. Telomeres contain no genetic material. They are on the end caps of the chromosomes inside every cell inside your body. And if we were in the right laboratory, we could actually zoom in and look at yours. Pretty radical. And by looking at your telomeres, we can actually see how old you are. Remember we talked about functional age, how it's not just a number? Like, yes, you might be 32, but you might have the chromosomes of an 18-year-old. Think of telomeres and aging sort of like rings on a tree. We can chop down a tree and count the rings and see how long it lived, right? Oh, this tree sat through the Civil War. Well, we can look at your telomeres and predict how old your body is. Think of it like this. Every single time a cell replicates, I always picture it in kind of a morbid way, like a guillotine. Every single time your cells replicate, a little bit of your telomeres come off, and a little bit more, and a little bit more, and as the years go by, your telomeres slowly get shorter and shorter and shorter. When there's no telomeres left, what happens to the chromosome? It dies. It can't hold together. Those end caps, think of them like, I don't know if I'm looking at your shoes, Think of them like at the end of your shoelace, right? There's a little cap. You ever have one of those come off and then try to lace your shoe? It doesn't work because the shoestring just gets all frayed and crazy, right? That's exactly what happens to your chromosomes when the telomeres go away. So you need these. But telomeres, as you age, slowly get whittled down and whittled down and whittled down. Let me show you what I'm talking about. Some of you have probably heard of telomeres, some of you have not, but this will maybe let it hit home, especially with regards to aging.
During this year's multi-generational research, Robert, who has spent his career documenting stress's effects on the individual and on the cell, tracks the trail of stress even deeper into our bodies.
One of the most interesting new directions of stress research is taking the effects of stress down to a nuts and bolts level of how cells work, how genes work, that half a dozen years ago nobody could have imagined.
The once unimaginable genetic structures called telomeres, which protect the ends of our chromosomes from fraying. As we age, our telomeres shorten.
What's interesting is stress, by way of stress hormones, can accelerate the shortening of telomeres. So the assumption is for the exact same aged guys, if you're a low-ranking guy who's just marinating in stress hormones, your telomeres are going to be shorter.
So how does this formidable finding apply to us? San Rafael, California. Once a week, Janet Lawson keeps a very important appointment. She joins other mothers who share circumstances that produce chronic, unremitting stress.
But she lost her balance, and that's the scary part. So we just went out and actually last night bought a new helmet just for fun.
And as she's getting older and wanting more independence, it's getting harder.
Each of these women is mother to a disabled child.
And for us, my son's only 8, and there's enough I can handle, and I don't allow myself to go too much out. I can't. I had a friend recently who said to me, I think you really should consider putting Lexi in a home. And that was really stressful in and of itself to think, wow. So, sorry. So I was like, wow, how can you even say that? She's, a girlfriend. She's, even though she can't really communicate, she loves. She loves. She loves.
These remarkable women came to the attention of biologist Dr. Elizabeth Blackburn.
I didn't directly know the individuals, but I know the stories. I'm a mother myself, and so when I heard about this cohort, I really thought it was worthwhile finding out what really is happening at the heart of the cells in these mothers who are doing such a difficult thing for such a long time.
Dr. Blackburn is a leader in the field of telomere research.
We have 46 chromosomes, and they're capped off at each end by telomeres. Nobody knew in humans whether telomeres and their fraying down over life would be affected by chronic stress. And so we decided we would look at this cohort of chronically stressed mothers, and we decided to ask what's happening to their telomeres and to the maintenance of their telomeres. What we found was the length of the telomeres directly relates to the amount of stress somebody is under and the number of years that they've been under the stress.
Such stressed mothers became the focus of a study by Dr. Blackburn's colleague, psychologist Alyssa Eppel.
Mothers of young children are a highly stressed group. They're often balancing competing demands like work and child-rearing, and often don't have time to take care of themselves. So if you add on top of that the extra burden of caring for a child with special needs, it can be overwhelming. It can tax the very reserves that sustain people. And if they're stressed, if they report stress, they tend to die earlier.
These women have shortened telomeres, decreased activity of this enzyme, and very, very rough number for every year you were taking care of a chronically ill child, you got roughly 6 years worth of aging.
This is real. This is not just somebody whining. This is real, medically serious aging going on, and we can see that it's actually caused by the chronic stress.
But there is hope. Dr. Blackburn co-discovered an enzyme, telomerase, that can repair the damage.
It's what I always call the threat of hope.
Preliminary data suggests that a meeting of minds such as this may actually have a health benefit by stimulating the healing effects of telomerase.
Yeah.
So she's talking about like a way to make your body produce more of it.
Telomerase?
Yeah.
Absolutely. We actually know a couple ways that you can do that. So I'm glad you asked. It's a good question. Yeah, so it's not all bad news. Along the way, they discovered, hey, there's an enzyme in our body that actually helps protect it. So it's not like it just keeps whittling away and there's nothing you can do about it. But it is pretty wild. So I think I emphasized last week, and those videos you watched, well, most of them, except for the one where we're trying to turn people into robots, stresses the idea that one key to living longer isn't necessarily trying to unlock immortality and try to live forever. It's all about slowing down the aging process, because these are processes that are happening inside our body, and maybe there's a way we can just hit the brakes and make it last a little bit longer. This shows you exactly what the opposite of that is. It's pretty wild to think when you're really stressed out. So just take this to heart. When you're under a lot of stress, the aging process inside your body is going into hyperdrive. You're accelerating you getting to the finish line, essentially. And when you're dealing with your stress, you're slowing that down, right? It's kind of a weird way to think about what's happening inside your body. Because when you're under stress, those telomeres are just getting whacked off and whacked off. So what can you do about it? Well, we've actually found a few ways that helps promote telomerase. This is good news. And the first is something that you might not have thought of: humor. Positive emotions and laughter through humor helps promote the production of telomerase. If you're curious, I actually teach the psychology of humor on Tuesdays and Thursdays. It's too late to join the class now. Callista's like, what? A second way, which I talk about a lot in my abnormal psych class, is something called mindful meditation. You may have heard of this, you may have not have heard of it. It's not just a hot psychology term that floats around. It's an actual practice that we teach in the therapy room for people to deal with anxiety and stress. And then also endurance exercise, things like long distance running, swimming. 3 activities that actually help promote the production of telomerase, which is an enzyme, which again attaches onto the telomeres and helps repair some of the damage that's been done. So, an interesting way you can actually see this in action. This is something that a lot of people always point out. Again, this has nothing to do with anyone's political affiliation, but I'm going to assume, as long as the person there is actually taking the job seriously, that being a president is kind of stressful. I don't really know how much fun it would be, because you're probably constantly doing stuff, right? Constantly, every single day, you're this, you're there, you're doing things. No, it's been known for a long time that when you're in that office, when they leave after 4 or 8 years, they are just, I'm done. I'm done. I don't want to do that again. It's like a buzzsaw you get into. But look what happens. These are not 8-year-old pictures. This is after just 3 to 4 years of being in the office. Bill Clinton entered sort of a handsome, I guess, middle-aged guy, and he came out your grandfather in just 3 or 4 years. So you can actually see this happening to people. This is the younger George Bush. His dad is actually a much better example, but I can't find a side-by-side, so I had to rely. But still, this is just, look at that. That's insane. His hairline, everything has changed. And then Barack Obama, of course, went in, kind of a slick-looking younger guy. And again, he turned into a grandfather in just 3 to 4 years. 3 laps around the sun, and boom, it looks like you aged about 10 years. If I had to guess, that's what I would say that is, but it's not. It's just your telomeres in action. So, any questions here? Quasi-program theory, and they've got some data to back it up, but there is another camp that says, hold on, there's something we can do about this, and this is our random error, folks. Aging, to random error camp, is not a disease. That's a little bit of a misnomer. Aging is actually a series, a set of diseases. There's a lot of things happening inside your body, and if we can just find the right ones to attack, maybe we can, again, slow down. That's what it's all about. Not sure about living to 300, but maybe we could live a quality life up to, say, 150. Like add on another 20, 30 years of quality life. And if you watch, especially the videos with Aubrey de Grey in them, he's the guy with the really 8-foot-long beard. I would love to have like coffee with that guy just to pick his brain a little bit. He told you about a whole host of diseases. I mean, there's so many going on, but we'll just pick a few that are all interrelated that are happening inside your body right now. One of them is something called cross-linking. So we'll call this 3 diseases of aging, put it that way. Cross-linking is actually something that you will eventually, I mean, I'm looking around the room and I don't see anyone who's actually noticeably experiencing this right now. Don't worry, it'll happen soon, maybe 8 to 10 years or so. It's usually around the age of 30 when people start to notice this. What is cross-linking attack? Some of you might know, because they talked about it a little bit. Cross-linking has to do with your skin. Have you ever watched a commercial? Literally, for any beauty product everywhere, they always mention collagen. This is only $79.99. It contains 10 times more collagen than the leading product. Collagen is a protein inside your skin. It's actually in the epidermis. You don't need to know that quite yet. But it's a protein, and what it does is it holds all of your connective tissues together. That's what it is. It's a protein that just holds you together, from your tendons to your muscles to your skin. But the most obvious place to see it is in the top layer of your skin. And this is a terrible drawing, but this is essentially what it looks like. If you zoom in on the molecule, it looks like little ladders, all straight and all in a line, nice and smooth. And it's the protein that when you go like this, boom, your skin just, I guess mine's still working just fine. Your skin goes right back, right? It helps keep your skin nice and elastic and nice and smooth. Don't we all want that? Smooth, elastic skin. We want to keep that. That's all every single beauty product tries to make your skin do. Smooth it out and keep it nice and soft and moist and all that wonderful stuff. But as we get older, something naturally happens, and it's called cross-linking. And this is what happens. Every so often, these things are replicating, right? Again, and again, and again, and again. And every so often, one of these little rungs of the ladder falls off and connects to the other one. Maybe like that, maybe like that. We call this, that's why we call it cross-linking, because the collagen molecules start to attach to each other. And when that happens, they don't function correctly, and your skin starts to become really rigid, and it loses all of its elasticity. Yeah.
From radiation.
That will absolutely. In fact, the first part of your online lecture is going to be about the skin. So if you want to accelerate this process, and it is actually frightening. Actually, a couple of years ago, I had a girl swear she would never go to a tanning bed again after the lecture on the skin that we did, the crossing, because especially she was very fair skinned too, and she's like, oh my God, I'm never stepping foot into one of those again. Yeah, the UV, the sun, I mean, it all depends on you and how much natural built-in protection. Someone who has darker skin tones is like naturally protected to begin with. But yeah, if you're really fair skinned, this process, just walking outside speeds up the aging process, which is a weird thing to think about, at least in this regard. You're exactly right. So cross-linking, these things just get locked together and they don't work anymore. Now there's really no way to untangle them. So you can buy all the products that you want, and no product is going to seep inside your skin and magically repair the collagen that's inside your body. It's just a scam. The second one, and these are all interrelated, free radicals. You've probably heard of this. If you've ever seen any commercial anywhere for grape juice, they talk about this a lot. Drink this and reduce the amount of free radicals inside your body. Right? What is a free radical? You want to know? What's that? An unpaired electron. What it is, in a nutshell, it's a waste product. He's exactly right. When an electron breaks off, it starts to float around your body, well, that's a waste product. Even the little bit of thing you're doing right now, some of you are just leaning back and typing, and you're breathing. Maybe you're writing something down. Every little minute human action that you take is a process, and it creates a waste product inside your body. Everything that you do. And your body, luckily, has other things inside your body that clean that up. You have little janitors inside your body that take care of the waste products, just like the janitors in T&H that come in here. Well, slowly over time, these just build up, right? There's only so much you can do. You ever have a new car or sit inside a new car? It's beautiful, right? It smells, everything's perfect, it's smooth, it's clean. And you can buy that car, and you can, if you drive it, but what's going to happen slowly over time? Even if you clean it every day, there's going to be little cracks, little things, little bits of dirt inside cracks that you can't get out, right? It happens. Same thing happens inside your body. Even the perfectly maintained body is going to build up waste products slowly over time. We call these free radicals. Well, free radicals can also do this. They can make the cross-linking happen. Because what if one of those molecules knocks into the rung and knocks it off? Boom, then you have cross-linking. What if some of the waste products gets inside the wrong part of the cell? It can kill that cell and make that cell die. So free radicals are not something that we want. They accelerate the aging process. Antioxidants, of course. Antioxidants is a natural chemical inside your body that helps destroy these waste products. So products that contain antioxidants, I had some blueberries for breakfast. Those contain a huge amount of antioxidants. So that is true. If you consume natural antioxidants, you are helping your body get rid of free radicals. So that part we can help ourselves attack a little bit. And then last but not least, again, all related, something called error catastrophe, which sounds horrible because it is. Error catastrophe is simply mutations. That's what it is. Mutations inside the body. Your chromosomes, your cells, they're all replicating. Well, every so often, it doesn't replicate perfectly. Something mutates. 48 times your cell replicated exactly like it should, but that 49th time something went wrong. Maybe because of a free radical. That's possible. They can cause mutations as well. So error catastrophe leads to things like cancers and other diseases because something didn't replicate in the right way at the wrong time. And it started a chain reaction inside your body that led to one part getting hurt, deteriorating, debilitating, whatever it is. So 3 diseases. And here's where I want to zoom in just a little bit. So if you haven't watched them yet, I'm assuming you have, but just in case, just a couple quick takeaways. Anytime. The Wine RX video, which resveratrol. What is resveratrol? Just to make sure you were paying attention. This was the big takeaway. And I actually remember when this came out, it was like, oh my gosh, someone has discovered a chemical that we're all going to take in like 10 years in a pill, and we're all going to live to be 200 years old. We're going to be super athletes. This is great. What the heck is resveratrol? Remember? Oh, good. Nobody. Oh, what? Now you're getting all fancy. No, it's fine. The sirtuin. What the heck is the sirtuin gene? This is actually important. This is all going to be connected. You're right. You're exactly right. So be proud of yourself. So resveratrol is a chemical that is found mainly, one of the main places it's found naturally is in the skin of a grape. Which is why they called it Wine RX, because concentrated red wine has very high levels, relatively speaking, of resveratrol. What they found is resveratrol extended the lifespan of mice. And not only did it extend their lifespan, their immune systems were amazing, and they lived very robust, healthy lives a good percentage longer than their counterparts. And so everyone got excited. And drug companies purchased, oh my God, it's like $750 million. These scientists got paid for discovering this because they were going to start this company that was going to change the world. But what happened in the research with humans? Did it work? And this is the big takeaway. No, I mean, we're not all living to 200. No, this is like 20 years old now. No, unfortunately, it didn't work. So resveratrol, the findings in mice, I guess, glad to be a mouse. Give me the resveratrol. But the findings from mice did not translate into humans. So it was really exciting. And in fact, you can go to Walmart and you can buy this now. It's like $2.99 for a big tub. Oh, I've heard of this. But it's not going to do anything for you. So resveratrol is one of those moments where we got really excited. And really, I wanted you to see that because it's an example of, trust me, people are working on this. They're trying to crack the code. And there have been moments where we've been really excited. We're in one right now. And that's what these little worms have to do. Hopefully you watch that one as well. But what about this? There actually is something that we know is holding up in the science. They were just starting to be studied, the skinnies. Remember these people? These were the people that were putting baby food on toast and having a party. Exactly. That's the problem. The skinnies practice something known as calorie restriction. And this is where you were going to see a bridge to these worms. Trust me, there's a connection. These are people who are purposely, what's the word? Sort of in like an eternal state of fasting. I think they said they eat about 600 to 800 calories per day. And it shows they're very skinny. But I know you're like, what the? But here's the takeaway. Their immune systems are very robust. They're not getting sick. They've been now followed for about 30 years. They are living longer and healthier. Are they going to live beyond like the 110 and 105? No, there's nothing to indicate that they're still not aging. But they are showing fewer signs of the aging process. But I'm not sure if you caught it, but the guy that was narrating the story kind of hit exactly kind of what Calista is saying is, okay, so you're telling me to do this, what is this a good trade-off? Like my life is kind of miserable from a lot of people's perspectives. Unless you're really into this and it's your thing, okay, yeah.
Actually, do a little research about this kind of stuff.
Yep.
There's this one kind of cool case too about this guy that was like 600 pounds. And for the full year, he didn't eat anything but the vitamin and droplets. He lost, I think, 450 pounds. But it was weird too because, like, you know how like, people lose a lot of weight, they have like the skin folds?
Yes.
He didn't have any of that.
Huh.
They say like the biology behind it is like why it's like healthier and stuff is because like when you consistently lose a lot more waste when you're fasting, you like finally use all that waste.
Yeah. Well, that's why people do intermittent fasting. I'm not sure if any of you have ever tried that or practiced that. It's becoming more popular. A lot of people do it incorrectly, which actually kind of throws their body off, and then it causes even more problems. But intermittent fasting does work if you do it correctly, and it does help you burn. Your body goes into, well, it's kind of a running theme. You talk about the sirtuin gene. We'll get into that in about 5 minutes. There are ways that we know of to sort of tap into, at least momentarily, your body's ability to, I guess, put it in survival mode, where it burns a lot more fat. I mean, that would be a case where it's obviously beneficial. If you knocked off, I have to look that up. So the skinnies, calorie restriction, there does seem to be some benefits from this. But let's zoom in on the worms, these C. elegans, and Cynthia Kenyon's research. This is still relatively new. And in fact, this sounds really nerdy. I'm not going to go to it, but there's now a C. elegans international conference every year because of this research. Conference of worms. But what were they able to do? They were able to, take these worms. This is pretty wild. They made one little change inside one gene inside these worms, and they were able to extend their lifetime by 30 times. That's pretty radical. And if you don't know what these things are, you didn't write it down, we're going to zoom in on this really quick. I'm actually going to show about 3 minutes of maybe what's the most important part of her video.
Okay, so those are hints suggesting that humans are susceptible to the effects of these hormones for aging. So the next question, of course, is there any effect on age-related disease? As you age, you're much more likely to get cancer, Alzheimer's disease, heart disease, all sorts of diseases. It turns out that these long-lived mutants are more resistant to all these diseases. They hardly get cancer, and when they do, it's not as severe. So it's really interesting, and it makes sense in a way that they're still young, so why would they be getting diseases of aging until they're old? So it suggests that if we could, have a therapeutic or a pill to take to replicate some of these effects in humans, maybe we would have a way of combating lots of different age-related diseases all at once. So how can a hormone ultimately affect the rate of aging? How could that work? Well, it turns out that in the DAF2 mutants, a whole lot of genes are switched on in the DNA that encode proteins that protect the cells and the tissues and to repair damage. And the way that they're switched on is by a gene regulator protein called FOXO. So in a DAF2 mutant, you see that I have the X drawn here through the receptor. The receptor isn't working as well. Under those conditions, the FOXO protein in blue has gone into the nucleus, that little compartment there in the middle of the cell, and it's sitting down on a gene binding to it. You can see one gene. There are lots of genes actually that bind on FOXO, and it's just sitting on one of them. So FOXO turns on a lot of genes, and the genes it turns on includes antioxidant genes, genes I call carrot giver genes, whose protein products actually help other proteins to function well, to fold correctly and function correctly. And it can also escort them to the garbage cans of the cell and recycle them if they're damaged. DNA repair genes are more active in these animals, and the immune system is more active. And many of these different genes we've shown actually contribute to the long lifespan of the DAF2 mutant. So it's really interesting. These animals have within them the latent capacity to live much longer than they normally do. They have the ability to protect themselves from any kinds of damage, which we think makes them live longer. So what about the normal worm? Well, when the DAF2 receptor is active, then it triggers a series of events that prevent FOXO from getting into the nucleus where the DNA is. So it can't turn the genes on. That's how it works. That's why we don't see the long lifespan until we have the DAF2 mutant. But what good is this for the worm? Well, we think that the insulin and IGF-1 hormones are hormones that are particularly active under favorable conditions in the good times, when food is plentiful and there's not a lot of stress in the environment. Then they promote the uptake of nutrients. You can store the food, use it for energy, grow, etc. But what we think is that under conditions of stress, the levels of these hormones drop. For example, having a limited food supply. And that, we think, is registered by the animal as a danger signal, a signal that things are not okay and that it should roll out its protective capacity. So it activates FOXO. FOXO goes to the DNA, and that triggers the expression of these genes that improve the ability of the cell to protect itself and repair itself. And that's why we think the animals live longer. So you can think of FOXO as being like a building superintendent. So maybe he's a little bit lazy, but he's there, he's taking care of the building, but it's deteriorating. And then suddenly he learns that there's going to be a hurricane. So he doesn't actually do anything himself. He gets on the telephone, just like FOXO gets on the DNA, and he calls up, the roofer, the window person, the painter, the floor person, and they all come and they fortify the house, and then the hurricane comes through, and the house is in much better condition than it would normally have been in. And not only that, it can also just last longer, even if there isn't a hurricane. So that's the concept here for how we think this life extension ability is.
The audience looks just as good. So what does this all mean for you? Well, here's how this is working inside the body, and then we'll move on to something else. So it's all back there. So you have this receptor on your cells called DAF2. When you just living a normal life, DAF2 is active. And one thing that it collects and puts inside the cell to help your cells work and function like they need to is insulin. You take in food, you take in nutrients, insulin comes inside your cell versus the DAF2. It catches it, brings it inside the cell, and everything works like it should. So here's the big catch-22, and this is where the science of aging and trying to unlock this always finds itself getting caught. On one hand, we need to eat. We need nutrients, right? We have to bring things inside our body for our bodies to function. Unfortunately, part of functioning is wear and tear, right? This is a process, and it don't only last so long. It's sort of like, okay, I got this brand new car, I'd like to drive it. Well, the catch for that is every time you drive it, you're putting a little wear and tear on the car, right? It happens, and and inevitably, you are bringing that car slowly to the end of its lifestyle or damaging it in some way. Same when we're functioning. It's great and we need it. Well, if we shut that off, if we can block DAF2, then this thing called FOXO appears. It turns on. And here's the little list of FOXO. When FOXO switches on, our caregiver cells are more active. This helps prevent mutations and things like cancer. That's what those caregiver cells do. Your immune system is boosted, so you're less likely to get sick. Growth hormone is produced inside your body, which helps repair your body. And then also antioxidants are produced inside your body. So all the things that we just talked about. The sirtuin gene, by the way, that we talked about with resveratrol, helps make FOXO active. The sirtuin gene is very active during puberty. Helps all these things happen. So the quasi-program theory is accurate. When we go through puberty, times of development, FOXO is very active. The catch is, in order to activate FOXO, you've got to be in some type of strife, right? You've got to be Tom Hanks in Castaway, stranded on an island, unable to eat. But this is why the calorie restrictors, the skinnies, show some levels of activation of FOXO. And the last bit before I make a leap to something different, we also know that when we study people like Mr. Overton, remember he's 112 years old when he passed away, centenarians and people that live well into their 90s and into their hundreds show heightened levels of activity of FOXO and more mutations in the DAF2 receptor. So there's something to this. In other words, we could study you right now. One, we could look at your telomeres, that'd be fun, see what your functional age is there. But we could actually look at your genetic code and look at your DAF2 receptors. If you have more mutations there and they're actually not functioning as well as someone else's, that's actually good news for you in terms of longevity. So this would be a mutation that you would actually want inside your body if you'd like to live longer. So it's interesting stuff. But we're closing the door on there, and this is just absorb this. There's nothing to write down. This is just to make a bridge into the next chapter. So just a quick, and now that we've gone over all of this, all the stuff that we've done so far, a lot of what you're going to see in here, I think will make a little bit more sense. And then we'll launch into, the next chapter.
In 1997, a French woman named Jeanne Calment passed away after 122 years and 164 days on this earth, making her the oldest known person in history. Her age was so astounding that a millionaire pledged $1 million to anyone who could break her record. But in reality, living to this age or beyond is a feat that very few, maybe even no humans, are likely to accomplish. Human bodies just aren't built for extreme aging. Our capacity is set at about 90 years. But what does aging really mean? And how does it counteract the body's efforts to stay alive? We know intuitively what it means to age. For some, it means growing up, while for others, it's growing old. Yet finding a strict scientific definition of aging is a challenge. What we can say is that aging occurs when intrinsic processes and interactions with the environment, like sunlight and toxins in the air, water, and our diets, cause changes in the structure and function of the body's molecules and cells. Those changes in turn drive their decline and subsequently the failure of the whole organism. The exact mechanisms of aging are poorly understood,
But recently, scientists have identified 9 physiological traits, ranging from genetic changes to alterations in a cell's regenerative ability, that play a central role. Firstly, as the years pass, our bodies accumulate genetic damage in the form of DNA lesions. These occur naturally when the body's DNA replicates, but also in non-dividing cells. Organelles called mitochondria are especially prone to this damage. Mitochondria produce adenosine triphosphate, or ATP, the main energy source for all cellular processes. Plus, mitochondria regulate many different cell activities and play an important role in programmed cell death. If mitochondrial function declines, then cells, and later on whole organs, deteriorate too. Other changes are known to occur in the expression patterns of genes, also known as epigenetic alterations, that affect the body's tissues and cells. Genes silenced or expressed only at low levels in newborns become prominent in older people, leading to the development of degenerative diseases like Alzheimer's, which accelerate aging. Even if we could avoid all these harmful genetic alterations, not even our own cells could save us. The fact remains that cellular regeneration, the very stuff of life, declines as we age. The DNA in our cells is packaged within chromosomes, each of which has 2 protective regions at the extremities called telomeres. Those shorten every time cells replicate. When telomeres become too short, cells stop replicating and die, slowing the body's ability to renew itself. With age, cells increasingly grow senescent too, a process that halts the cell cycle in times of risk, like when cancer cells are proliferating. But the response also kicks in more as we age, halting cell growth and cutting short their ability to replicate. Aging also involves stem cells that reside in many tissues and have the property of dividing without limits to replenish other cells. As we get older, stem cells decrease in number and tend to lose their regenerative potential, affecting tissue renewal and maintenance of our organs' original functions. Other changes revolve around cells' ability to function properly. As they age, they stop being able to do quality control on proteins, causing the accumulation of damaged and potentially toxic nutrients, leading to excessive metabolic activity that could be fatal for them. Intercellular communication also slows, ultimately undermining the body's functional ability. There's a lot we don't yet understand about aging. Ultimately, does longer life as we know it come down to diet, exercise, medicine, or something else? Will future technologies like cell-repairing nanobots or gene therapy artificially extend our years? And do we want to live longer than we already do? Starting with 122 years as inspiration, there's no telling where our curiosity might take us.
All right. That is a good way to close out. Well, we're going to call it grounding. What is that? All the theories, all the theoretical stuff, foundational stuff, we're done with that. And from now on in this class, we'll talk about actual changes that are happening to you, around you, to your relationships, your body. And that's where we start. So we're leapfrogging over chapter 3. We actually just kind of skipped that, so sorry. If you read it, if you really liked it, it's still yours. You can still read it inside the book. But we're leapfrogging over that, and we're starting in the place that most people think of when they think of getting older, which is, and maybe this is shallow, but how you look, right? Your appearance. Those the physical changes that happen inside your body. That's what chapter 4 is all about. I guess it's not all about appearance. And in fact, I start in a place that maybe outwardly has nothing to do with actually how you look, but maybe just how you function. And that is changes in our sleep patterns and what that may or may not mean for you as you get older. So let's just be a health pamphlet for a second. How much sleep do you need? 7 to 8? Does that sound about right? So you can write this down. So So right now in your life, as an adult, you need about 8 hours. Did you know how much sleep does my daughters need? They're 9 and 13. Is it 8? No, but a lot of parents think this, and they let their kids stay up till like midnight. Oh, they got to get up at 8. That's 8 hours, right? A younger kid needs about 10 to 11 hours of sleep per night. What's that?
Like LeBron and like
right? It's interesting you mentioned LeBron. I remember what's popping into my head. I've been talking a lot to my old, well, he's not old, but my cross country coach from high school. I have this memory seared in my head, and I don't know how it got seared in my head. I guess it just meant something to me. I was lucky to go to school with a really, crazy gifted runner. He was my friend. He's still my friend. His name's Jim. Olympic trials, just amazing. From a small town, it was just like lightning in a bottle. Like this kid was just amazing. Great teammate. And I remember my coach, Dan, one day, he was talking to him like, what makes Jim different? And he said, I'll tell you what his secret weapon is. I'm like, what? Sleep. That kid sleeps every night like clockwork. By 8 o'clock, he's in bed. 10 to 12 hours a night, every single night. That's his secret weapon. And I never really understood it until I started learning more about sleep. And yeah, it's true. Elite athletes sleep a lot. And there's a really good reason for that, which actually might make sense. Not by the time you leave today, because we're going to end right where we left on Tuesday, and it was somewhere in the middle of this. But so what about older people? Do they need more or less? So when I say older, I mean those 65 plus people that you talk to in your interviews, which by the way, really good job. Those are really, really fun. About halfway through, really fun to read. And it sounds like you guys actually got a lot out of it already in this first one. But well, before you answer that question, how do your sleep patterns change? Like, what are the stereotypes inside your head about really older people and sleep? They do. That's actually true. So they get up early. They're right at Denny's, right? 6 in the morning. Oh, I always make that noise. So do they need more sleep or less sleep? Less sleep. So that makes sense, right? It's actually one of the big myths of sleeping. So older people actually need just as much, again, to maintain a healthy lifestyle as you do right now. 7 to 9 is still the recommendation if you're 90 or 109. That doesn't mean they always get it because of natural changes that happen inside our sleep cycle. So just like things naturally change to our legs and muscles and our eyes and our ears, things are happening that kind of screw up our sleep cycles as we get older, but we still need it. So this is going to be a quick primer, like literally quick. When I teach intro to psych, we spend a whole week on sleeping and dreaming. So I'm going to try to do this in about 2 minutes. Some of you may know this. So some of you, maybe you haven't talked about this in 2 years because you took Psych 110 2 or 3 years ago. But here's how sleep works, if you didn't know. I'm just going to draw something really quick. These are really, really rough drawings. So just excuse me. There we go. Now we're really slowing down. So one thing that happens as you fall asleep is your brain activity slows down. Maybe you already knew this. That's just a picture to show you the brain activity inside the brain as you go from stages 1, 2, 3, and 4. And when we get into 3 and 4, we start to call that deep sleep, right? So in stage 1 and 2, that's when you're nodding off, you're easily woken, but you're still technically asleep. But your brain slows down, your body slows down, your respiration slows down. And a sleep cycle looks like this. It seems a little bit counterintuitive, right? Over a period of about 45 minutes, you go from stages 1 to 4, right? Your body's slowing down. And then you enter this thing called REM, right? Not so much. What? Here, I shouldn't have said yes. What happens is you actually make a U-turn and you start going back up. But something really weird happens, and we actually don't, if you're interested, we actually don't know all the mechanisms that make this happen. Instead of waking up, because you're making a return journey, instead of waking up, you suddenly go into what we call REM sleep. You stay there, and this is important to know. You stay there for about 10 minutes, And by the way, this is when most people report having those vivid dreams that are like hyper realistic, full of emotion, usually some type of intense emotion. And then the cycle repeats itself. So in a good night's sleep of about 8 hours, you're getting about 8 cycles. Well, it's actually 5 or 6 cycles usually because it changes. The length of these change as you go. Let's say anywhere from 5, we'll just call it 7. Well, we've got 7 good sleep cycles per day without waking up. That's the key. And we call this your sleep. This is the natural sleep cycle. But the myth is that we need less. I'm not going to get to that 50%. But really quick, I like these little short videos. They explain a lot in a brief amount of time.
In 1965, 17-year-old high school student Randy Garner stayed awake for 264 hours. That's 11 days to see how he'd cope without sleep. On the second day, his eyes stopped focusing. Next, he lost the ability to identify objects by touch. By day 3, Garner was moody and uncoordinated. At the end of the experiment, he was struggling to concentrate, had trouble with short-term memory, became paranoid, and started hallucinating. Although Garner recovered without long-term psychological or physical damage, for others, losing shut-eye can result in hormonal imbalance, illness, and in extreme cases, death. We're only beginning to understand why we sleep to begin with, but we do know it's essential. Adults need 7 to 8 hours of sleep a night, and adolescents need about 10. We grow sleepy due to signals from our body telling our brain we are tired, and signals from the environment telling us it's dark outside. The rise in sleep-inducing chemicals like adenosine and melatonin send us into a light doze that grows deeper, making our breathing and heart rate slow down and our muscles relax. This non-REM sleep is when DNA is repaired and our bodies replenish themselves for the day ahead. In the United States, it's estimated that 30% of adults and 66% of adolescents are regularly sleep deprived. This isn't just a minor inconvenience. Staying awake can cause serious bodily harm. When we lose sleep, learning, memory, mood, and reaction time are affected. Sleeplessness may also cause inflammation, hallucinations, high blood pressure, and it's even been linked to diabetes and obesity. In 2014, a devoted soccer fan died after staying awake for 48 hours to watch the World Cup. While his untimely death was due to a stroke, studies show that chronically sleeping fewer than 6 hours a night increases stroke risk by 4.5 times compared to those getting a consistent 7 to 8 hours of shut-eye. For a handful of people on the planet who carry a rare inherited genetic mutation, sleeplessness is a daily reality. This condition, known as fatal familial insomnia, places the body in a nightmarish state of wakefulness, forbidding it from entering the sanctuary of sleep. Within months or years, this progressively worsening condition leads to dementia and death. How can sleep deprivation cause such immense suffering? Scientists think the answer lies with the accumulation of waste products in the brain. During our waking hours, our cells are busy using up our day's energy sources, which get broken down into various byproducts, including adenosine. As adenosine builds up, it increases the urge to sleep, also known as sleep pressure. In fact, caffeine works by blocking adenosine's receptor pathways. Other waste products also build up in the brain, and if they're not cleared away, they collectively overload the brain and are thought to lead to the many negative symptoms of sleep deprivation.
Now, this next part you're going to watch happens when you're in REM. So this is why REM, and this is planting a seed for what we'll talk about virtually.
So what's happening in our brain when we sleep to prevent this? Scientists found something called the glymphatic system, a cleanup mechanism that removes this buildup and is much more active when we're asleep. It works by using cerebrospinal fluid to flush away toxic byproducts that accumulate between cells. Lymphatic vessels, which serve as pathways for immune cells, have recently been discovered in the brain, and they may also play a role in clearing out the brain's daily waste products. While scientists continue exploring the restorative mechanisms behind sleep, we can be sure that slipping into slumber is a necessity if we want to maintain our health and our sanity.
Alright, and this is exactly where we stopped on Monday. So it's where we're gonna hit, I mean, it's time to go anyway, so that was beautifully, perfectly timed. End stream. There we go.